Let me now continue the 6th chapter, Elements of Models, in the module Models in Sciences, or how I would call it, Models to Model and Modeling, with a concentration on computer science. Let us first consider why we need a demarcation. What is a model? Why we need to have a characterization? What is a model being? But what we shall do in this case. Let's take a simple example, let's say from financial market analysis, and we have maybe a lot of pitfalls I took from literature. In, let's say, analysis, we have maybe too many factors we should consider. We have a dependence among all these parameters. Maybe we have not an equal behavior of parties. Maybe we have random noise. We have maybe bad data or not sufficient data. Maybe we have a too large time horizon. Maybe we didn't really consider all the knowledge we have about, let's say, such processes. Maybe we should also think about the influence of outside factors, parameters we should have incorporating into our model. And maybe we should use also some kind of stochastics probability theory for having an application of these models, for instance for forecasting or for retrospective reasoning. So for this reason we need to have really proper models. And now we have so far been tackling the specification of model elements, some principles, we have been considering the parameters, and we have been also considering how to compose a model, what could be a general composition theory. Now let's start with compliance. A model is of course based on some kind of analogy, and it should provide a service as an instrument that functions in a scenario. For this reason we can try to characterize a model by its capacity. The model provides some understanding of the original. The model provides an explanation or demonstration through auxiliary information. So in this case it makes the origins a little bit better to understand and to handle. The model provides an indication and facilities to make properties viewable. The model allows to provide variations and support optimization. The model supports verification and, for instance, of hypotheses. The model supports construction of technical artifacts or whatever is the function of the model. The model supports control and things in reality. The model allows replacement of things of reality and acts as a mediating means. These are somehow statements about the capacity, the same statements we could make about the potential of the model, but the statements are still a little bit too narrative in order to use them as a proper definition. Let's try to come to this topic by remembering the utility of an informative model. We should say, okay, fine, what kind of information we want to provide to the user. That means, what is the issue that can be solved with this instrument? What are the main ingredients of the instrument? And how they can be used? What is the main background behind the instrument? Why we should be aware of this main background behind the instrument? And of course we can now ask why we should at all use this instrument. We have been introducing the SMART and SWOT evaluation frame. Maybe we can use the SMART and SWOT in frame for evaluation to evaluate whether an informative model is of use. We can characterize this is of use using the capability maturity model. We say, okay, fine, a model is at maturity level 1, if it is given in ad hoc style, there are no best practices, the background is unknown, and there is no common understanding. That means in this case we have some kind of, the model has been developed on the fly, and for this reason maybe we didn't really develop it properly. Another one is maturity level 1. It is informal, but it is understood, at least at the specification level. Maturity level 2 allows us to use the model in a proper form as an instrument. That means in this case it should be somehow systematically made, and the results of our application of the model as an instrument should be somehow checkable, and the background is understood and goals are explicit. As you have seen in the first introductory example, already maturity level 2 is not really given. Maturity level 3 means, in this case, I'm the owner, I'm the performer of the model development, of the model utilization. So in this case, of course, we have practices to use the model in a proper form, practices to develop the model in a proper form. And of course, we know also how to improve the model. Maturity level 4 will be, I think, very seldom reached. We have control techniques. We know at least, or we are the head of the quality. It is fit for use according to the requirements we have to the functions of the model, according to the profile maybe, and we can also changes. Maturity level 5 is the highest level, and it means that the model can be without any problems improved, adapted. New functions, new application scenarios can be incorporated, and whenever we feel that the model does not do what we want, it can be easily improved, we can eliminate the mistakes or the flaws, and then we have some kind of evolution support. This would give some kind of evaluation framework. What is in general the capability dimension of a model and the maturity of a model? So we have in this case incomplete, performed, managed, established, predictable, and optimizing. Now we can step towards adequacy compliance. We have in our case a model consisting of, or specified on top of, some kind of scenarios where the model has some functions as an instrument, on top of a set of selected origins, the grounding, the basis, the context, the community of practice, adequacy and dependability. In reality, for this part, we should only consider the functions the model should play and the adequacy. That is a bit simpler. For this reason, we can say, okay, fine, then we can now have a procedure of checking and toughening the model according to the functions in scenarios that are really necessary and excluding those which are not really necessary. Then we have also a functioning story, and the model has a role and a play in the given scenario. In this case, we also might limit ourselves and attention to those origins that are really considered and exclude a good number of origins that we should not consider at all. Furthermore, we can work on how to strengthen a model. Of course, we should have only a minimal collection of representative origins. Later I will come to the approach to genericity or to reference models. And then in this case we can say, okay, fine, the adequacy is now given by analogy plus the focus plus the purposefulness. The focus should be given, allow us to describe the model at the level of abstraction that we really need. We should know the limitations of the parameters, the sufficiency of these parameters, the orientation on essential or relevant properties, the objectives to be represented in the model, And of course, the model should not an over-model or over-specification. Purposeful means, in this case, we have a set of methods. All these methods come with their biases that must be compatible and must be nicely and easily to integrate in our modeling story. And we have maybe methods and an application story. Okay, let's now step to adequacy as the most essential part, to analogy. Okay, analogy compliance. We have already based on there should be some kind of similarity of the model and the origin, depending on the purpose and the use. And in this case, we have to have an explicit similarity relation. And this explicit similarity relation is based on parameters we have been giving and considering. So it means in this case, we can have some kind of properties of this similarity relation. And then in this case, we can define in a proper form what means to be similar. Of course, this analogy should be regular. So we have exact rules within which the framework of a system can be used for derivation of properties. We might have to consider also some kind of fertility to the potential to produce as many as possible statements that relates to the capacity of the model. And of course, we want to have as simple as possible model. So in this case, we should look whether we can simplify the model by abstraction, by shortening, by concentration on essential and relevant parameters. In this case, we have now as the main property the similarity, as we have been introducing already in part or chapter 3 of the lecture, where we have been considering some kind of similarity measures. And in this case, we can say, okay, fine, given by a set of similarity measures, we can now conclude that this model is similar to the origin. Similarity, in any case, depends on the function the model plays as an instrument in a scenario. Okay, let's go to the dependability. Of course, dependability should be based on what we know from our origins. We should, however, also consider the driving directives of our models and the background. The background means in this case the grounding and the basis, and as well as the context, and of course we should please our community of practice, and for this reason we should consider it. And then we can derive some kind of dependability criteria. Okay, then in this case we have a number of issues we have to specify. Which justification and sufficiency is inherited from the grounding and basis. So we don't have to specify it explicitly. It can be somehow inherited from the grounding and the basis, and of course in this case we should know what the basis and the grounding provide. So in this case we have also a number of quality criteria, and also maybe restrictions to the quality characteristics due to the basis and the grounding. That means in this case we have some kind of common beliefs we have been underpinning under the model, and we don't repeat it anymore. We will later call these underpinnings deep model, or if we integrate also the Mould, matrix. Then we have a direct justification and sufficiency provided by the origins. The origins have their justification and their sufficiency, and we have already used a number of methods for the origins. So we should know this, and then in this case we can directly inherit whatever is given by the origins. Furthermore, we need an additional justification, of the model. I should come to it in the next slide. A specific sufficiency for the model, of course, in the restriction to the essential, relevant and computable characteristics. I will come to this a little bit later in chapter 15. We can use the framework Hertz was proposing for dependable utility. The model should be analog, that relates back to adequacy, admissible, functional, right, simple, dependable, and at least partially understandable. I relate to a very nice book written by Halun on the background in physics model. Okay, so in this case we have only to consider the additional justification compliance. Okay, then we can directly go for our 4 main properties of the justification. It should be corroborated. That means we have to have a reasoning calculus that provides us the corroboration. That means in this case we might have an argument calculus, or an attack defense calculus, or maybe some Y calculus. So in this case we can have some kind of a teaser or short explanation story as a narrative, of course with Hoxton's situation under consideration. And in this case we can have a corroboration in order to have a less context sensitive model. Rational coherence and conformity means in this case we have a proper relation of mutually associated model parts. It could be rational and orderly and consistent. In this case we have some kind of calculus. I would propose that someone uses in this case an abduction calculus that says, okay, coherence and conformity is caused by something. And then in this case we have a reasoning calculus that we say, okay, fine, since these conformance conditions are fulfilled, we can conclude by the abduction calculus that this is now rational, coherent and conform. One thing that is often forgotten about models and the justification of models is it should be falsifiable. We should have an ability to reason against problematic cases, exceptions, systemic and systematic errors. That is a part that we do in computer science with testing facilities, with validation and verification calculi. In all cases, this calculus is unfortunately non-monotonic. Whenever we add an element, we have to revise our calculus. Or at least the axioms and the statements that are used in the calculus. Furthermore, we can now say, okay, fine, since we have been properly selecting the set of origins using some kind of minimal representations or prototypical representatives of our origins, then we can say, okay, fine, we should maybe look for changes in the set of origins. That means in this case it should be evolution reconcilable. We have maybe a specific structuring of the model for the method application. Okay, then we can now go for sufficiency. Sufficiency compliance is of course based on the same criteria and parameters in our model being we have here. It's a little bit larger list than for adequacy. And of course in this case we can say now, okay, fine, we go for our dependability. We are using now only essential and not yet considered quality characteristics. Quality in use means we have the full capacity and potential so that the model is functioning in the given scenario as an instrument. That depends on the context, on the community of practice, on the way how we deploy the model, and maybe we have to add some additional characteristics for the added value specification. The external quality is now defined by the deployment parameters. maybe it should be at least evolution reconcilable. And we must have some kind of maybe model deployment infrastructure. And then we can directly derive which of the internal external quality characteristics can be used. And then we can also say, okay, fine, for internal quality, we use the characteristics that support that this model is really a model. That means it supports the model being. And then we can have evaluation procedures. I would not force everybody to go to metrics. We can also use some kind of logical reasoning calculi or some other calculus like numerical calculus that we are using in machine learning. Okay, this would be now the compliance. How to make it now? There is a pretty nice trick. Steal whatever you have been already properly developing. Noam Chomsky developed some kind of theory of government and binding and had in mind, in reality, genericity development in languages. What we do whenever we make a statement is we first in our brain generate some kind of concept map we would like to use in order to express what we think. And then we form the expression. And then forming the expression, we can also adapt the expression to the language, to the auditory, to a specific context. And in this case, you have some kind of general procedure. These are alpha and beta rules in the Chomsky theory. Genericity is a bit better, or generic models is a bit better than general models. General models are the most general principles we are using. We idealize as much as possible. It is not yet decided whether we can have a general model. A generic model is a bit different. It combines anything that we know so far, and for this reason it should have at least 5 main properties. They must be, of course, adequate and dependable. The quality of the generic model is well defined, so we can use it consciously. The property should be descriptive and not evaluative. That means we should have a real description of the properties. And they should be really flexible so that we can modify the model from time to time. And for this reason, the generic model is something like a first best guess. And then we can go for orchestration of our instantiable parameters via unfolding the model elements, followed by a model transformation, especially also a functionalization. I will show in the sequence in the later slides, and adaptation to the given infrastructure. This theory has been applied for generic workflows in the PhD by Marina Troman-Frick, recently defended at Kiel University. Generic workflows are workflows that allow adaptation to the circumstances but behave in somehow similar way according to maybe another generated workflow. Think about, for instance, about an organization like in hospital. It is somehow for investigation, for diagnosis, necessary to go to A, B, and C. Which order you go depends on the current circumstances. In the hospital, you go first to B, then to C, and then to A, because of somebody was already occupying A, and for this reason you cannot go directly to A. So in this case you have now a different sequence. And all these possible different ways how to do it can be combined in generic workflows that you say, okay, fine, A, B, C must be done somehow, and they are not really connected to each other. For this reason they can be done orthogonality in parallel form and orthogonal, and then you have it in a proper way given. Okay, we have a number of experiences with this kind of genericity and generic workflows. You have some kind of workflow abstraction. You can use maybe what we already know from languages, that you can build language sentences based in a framework. You can have also some kind of freedom of movement, like we do in storyboarding, like we do it also in movie business. Think about a remake of a movie. Then we have some kind of story space specification, and we use this experience for developing our models. That is similar to web information systems, where we have been developing a lot of different websites, almost more than 60. The background is a pretty funny thing. That is props morphology of tales, of fairy tales. You can also go to Veil for screen and television writing in storyboarding for the movies. That means in this case we can reuse anything what we have been using for developing of really sophisticated websites that support a user. The general theory of Chomsky is an approach to government and binding. I will make an additional video that explains in a little bit more detail, but I might give here some of the details only. First of all, we have a generic specification. Let's go for a database application. In the database application, I'm assuming that whenever the structure is given, the functionality that is needed by the user can be generated. And that means in this case, if we have a function properly specified according to the framework the database management system provides, then in this case we can translate the function to a corresponding operation that is directly computable in the database management operation system. Okay, then in this case we have now given a structure and maybe integrity constraints, maybe as static integrity constraints. And then we have, let's say, alpha rules for extending it by the functions. So these alpha rules are generated from some kind of generic functions, like for retrieval, modification, and service functions. And we can now incorporate directly these functions set as an algebra into our specification of our database application. And we can transfer the static integrity constraints to dynamic integrity constraints so that they can be checked by the functions. So in this case we have simply a ground schema, and then we can say, okay, fine, we have a mapping to any kind of database management system that behaves at least according to this kind of mold. The mold notion I will come in a minute as well, to this kind of methodology. The setting for generic workflows is nothing else as you describe, maybe on the basis of a CSB expression, or based on some kind of generic functions. You have given a context, you have maybe some applicability constraints, you have interactions, you have consequences, and you have strategies and maybe related generic workflows and can replace a given workflow. And in this case, you find you have a number of parameters, and these parameters can be instantiated, maybe enhanced, maybe by context, for instance, or maybe somehow specialized so that they are representing our situation a little bit more properly. Let's say a typical generic setting would directly lead to some kind of mini stories. A mini story is nothing else as a sequence of, or let's say at least a number of operations we can perform, or functions we can perform, and they form some kind of unit. For instance, we have a mini story in an e-business environment, advertise and quote. In this case, we represent the products. We may provide variations, so yes, that you can collect the appropriate product in the appropriate setting. We can also make some kind of collection support. So in this case, we have now the advertising and quoting. Then we go for requesting a response. Later, the user selects and maybe collects whatever has been somehow selected. Then we can go for bargaining, contracting, or for ordering the product, delivering and invoicing the product, and finally to pay. And in the problematic case, maybe also to return the product. That means in this case, we have a number of typical generic workflows that can be directly represented as a specification of the mini stories we use in e-business. Okay, then the main issue is now to have some kind of database functions that specify what we are doing. And in order to have an adaptation facility, we have, for instance, somehow adaptation, specialization ability that allows us directly to incorporate whatever is known from our origins. And we call now this adaptation functionalization. We take the structuring, we take the database schema, and we take a set of views. And then we say, okay, fine, the function application in this setting of this structure, of this kind of integral constraints, results in this kind of functionality, where we can even add the dynamic integral constraints, and maybe we have somehow a distinguished initial state, so we can start there. In this case, in a generic workflow, would nothing be else as now a functionalization given by the setting we have been developing there. Look, for instance, for database accessor. A database accessor is nothing else as it encapsulates the physical access to data without having any kind of details into a logical access, so that we can really reason on the language SQL. In the context, this is nothing else as we are using advanced ETL logics, a model view controller grid. The applicability is height, physical access, and maybe complexity, parameters or optimization and semantics. The structure is layered in proxy frame. The interactions come from sequence diagrams. The consequences are given as maybe limits of the application control of data access, or you have also maybe an independence from other users who are using also database access facilities. You have maybe also optimization, and maybe the order is can be somehow organized in a different form. And then you have our alpha and beta rules. And the alpha and beta rules say, okay, fine, you have the generic function, you get the model view controller grid, and from the model view controller grid you can directly derive the program. That is a general pattern how we are using now our access to databases. It is nothing else as a generic function that we can use for assessing our data. That means in this case we have now nothing else as we have given our alpha rules as general rules. We have maybe a way how we select our concepts we need really. We can pre-prepare them, and then we have a general pattern for transforming. We have an input, we have an output, we have some kind of supporting facilities, in this case some kind of information, and some kind of controlling facilities. And then you say, okay, fine, our transformer transforms the generic concept to some kind of maybe in object-oriented setting at least to class pattern. And then you can say, okay, fine, I go now with my beta rules, use this class pattern, have again some kind of supporting information that I can inject, have some kind of control rules, and finally I have my program I would like to have. That means in this case we have now applied the general human structure, how to assess those things. We will later see that our concept maps are really sophisticated maps and not really classical structures we are using in object relational database programming. And for this reason the alpha rules must transform now our web of notions, of concepts, to a proper concept structure, maybe expressed in an advanced entity relationship model, language setting, then in this case we can have now also better rules, and the better rules, okay, fine, now we transform it to those that can be directly provided on the basis of a specification for a database machine. Okay, the second thing what we want to use is some kind of mold. A mold is in mechanical engineering a container into which, for instance, some liquid is poured, and so we get, after the liquid becomes hardened, some figure. So in this case it means that we can use the mold to directly configure the corresponding structure, function set, controls of our system. In mathematics we have also such kind of molds. For instance, you go to differential equations, you have a number of forms how to solve a differential equation. Maybe in an analytic setting you want to have some kind of functions, some kind of approaches, some kind of methods that can solve these differential equations, and then you try, and this is a try and error process, you try which of the given methods works properly, and then you start to apply this method, and then you can finally have some kind of pretty nice, easy way to solve the differential equation in an analytical form. If you can't do it, you go to a numerical mold. So it means in this case a mold in mathematics is nothing else as a general and well-defined experience framework how a problem is going to be solved and how it can be faithfully mapped back to the problem area. Okay, then we can now define. Modeling is based on molds. That means in this case it contains the background, especially some parts of the grounding, some parts of the basis, on a, I would call it now, canon of methods for model development and model deployment, and on scenarios that determine the function a model should have in a given scenario as an instrument, and the play, how the model is used according to our context, according to the abilities, skills, ways how they are habits, how they are used in our community of practice. And of course the instrument properties that we have to anticipate. That means in this case we have again our compliance setting, what our model should do directly put into the mold. That means in this case we can now have, and I will come back in lecture 10 in the lecture on stereotypes of models, some stereotypes. A stereotype reflects the general approach. A pattern is a specialization of the stereotype. A template is an integration into what we want to do. In classical model-driven development, we start with a stereotype, that is our general expression. We develop a number of conceptualized, maybe, pattern, and then we map these pattern to some kind of program stubs so that we can directly inject whatever is necessary from our setting of parameters into the template, and then we can have as an output of such kind of computation a little program part that expresses anything what we wanted to do. That means in this case you have for each pattern a number of templates, and for each stereotype a number of patterns. And we can reason in the following way, that we say, okay, fine, the stereotypes are doing nothing else as representing our setting as a strategic background. The pattern specify tactics, and templates specify how we can operationally adapt the pattern to a given scenario of application in a given setting, in a given context, for a given community of practice, for a given set of origins, and of course this depends from the environment. In model-driven development, we say, okay, we have a pattern, and the pattern is something like a component of a model. That means we have a pattern as a general model, and then we say, okay, fine, we transform this thought to our platform-independent thinking, and then with the platform-independent thinking we can now adapt directly as a template this to a corresponding platform-dependent model. We will come back in lecture 14 to this kind of approach. Okay, now we can reason on how general it is. We can use first our analogy property. Maybe we have an analogy that is based on mappings. Then we go with our origins model suite. We derive a number of properties. We develop the objectives for the model. We develop our model somehow. In this case, we say, okay, fine. We have been using for our origins a language that has maybe some theory about objects, and for our mappings to the model we use maybe another language for declaration of representations of models, and then we develop a model. Oh, I have here a mistake. It should be M. So in this case we have now some kind of purpose invariance for our mappings as a main property. Okay, that is nothing else as a specific mold of constructing systems. We can also use now this mold for consideration of restrictions. In this case we can say, okay, fine, up to this kind of restriction, up to this kind of economic limitation, we develop our model. That means in this case we have some kind of guidelines integrated directly into the mold, and for this reason we might have also guidelines. What is means strictness? What means proper adaptation? What is the orientation of on functional aspects, time, functional space, or something like that? What is the abstraction of our quality parameters? What means strict evaluation? That means in this case we have some kind of true notion. What is adequacy of our models? What is the purpose, intention, benefit, and ethical issue? What is the abstraction of question of essence and meaning and objectives? So in this case we have now also directly developed an understanding of the limits of our modeling approach. What are the relative limits and what are the absolute and unchangeable limits? So we cannot overcome them. This is mainly based on the grounding and the basis, but also on the availability of methods. So finally I would like to go to representation, to visualization. There's a very nice website that shows a map of visualization methods. I have been writing here the reference to this website. You see we have a very different kind of models. We have a data visualization, we have some kind of visualization for information, we have some kind of visualization for concepts, for strategies, for metaphors, for compound elements. Let's now go over this set of visualizations in detail. First, maybe you have a visualization based on some kind of very abstract bubble chart, or maybe you can have it on a bar chart, or maybe even on a bubble map, like I show it here for the map of United States. Or you have maybe an area chart that shows an evolution, a development, a timeline, with different, let's say, areas where you show from which it depends. You might have this 4-square PCG matrix You might use, let's say, some argument map, in this case for information-based or information-oriented, information business, information systems. You can use also such kind of learning maps for representation, or might be you might have some kind of charts in the form of behaviour graphs, or maybe you have simply a mind map. Mind maps are very useful in order to show how a concept is composed of. You have again such kind of very abstract diagrams and charts, arc diagram, area graph, bar graph, box plots, brainstorm or calendar. You might have also something like in visualization using metaphors, like you have a brand iceberg, or maybe you have some kind of categorization, and in this case you can use an affinity diagram. You can also visualize things by other metaphors, like you have a bridge metaphor, and you can have a bridge of negotiation. Or you have maybe a very abstract form of a map, like the London metro map. It is of course not really showing the distances between the stations, but it shows very nicely how you can move from one station to another station, on which station you should commute. Or you have something like a data flow diagram showing you how the data is flowing. You can have also other abstract diagrams like condigrams in a spiral plot, or arrow bars, or Gantt charts. You can also have some kind of, let's say, onion shell approach, when you show the shells as circles. Or maybe you have some boxes that shows you some kind of two-dimensional representation. Or you can have a concept skeleton that is somehow mapped to a 2D plane diagram. The same would be for this kind of argumentation network. You might have also some kind of, let's say, visualization in the form of a geographical figure. Or you might have also some kind of 2D diagram of structures, like we use with some kind of entity relationship diagrams. Oh, das war falsch. Oh. Ja. Okay. Fourth part of 19. You have again abstract diagrams, charts, choroplasts, maps, circles packing, candlestick diagrams, bullet charts. You have maybe also some metaphor, like an argument is accepted. You have to make a claim, and the claim is now going down, and then it is accepted. So in this case, you can use this kind of little toy to represent how the argument is resolved. You might use also cartoons for the representation and visualization of models. Another representation are cluster charts, or communication diagrams, or let's say in an argument theory setting, cause-effect chains. Again, you might have another number of abstract diagrams, like heat maps, like Hikake pattern, like illustration diagrams, like Nightingale row charts, like point and figure charts. Or you use maybe some kind of approach to map different connections between and associations and flows. Or you might have such kind of a failure diagram that shows, like in an argument map, what is the cause for which kind of failure. You can also use a narrative setting, a narrative form, like a feedback diagram. One very nice setting is the so-called fishbone diagram, or Ishikawa diagram, that says, okay, fine, what is supporting and what is enabling something, and then in this case you can finally have maybe a result. Or you can use also an almost four-dimensional figure with a dilemma diagram. What is the input, what is the output, what is supporting it, and what is the reason for having this kind of dilemma. Furthermore, you have maybe some maps like decision trees or like histograms. With histograms you should be very careful whether the data are correct. You might have some data maps, again with abstractions, and then in this case you can use colors to differentiate the statements about areas and maybe some developments. You can have something for decision recovery where you have some input, you have some output, and you finally have some supporting mechanism. You might also use some graphs and some flow graphs like we have been showing here. Additionally, you have maybe some do not chart or some dot matrix or some flow chart or some flow map or some density plot or some connection map as a very abstract setting for visualization models. We can continue with Kage charts, with line diagrams and graphs, with Marimekko charts, with multiset bar charts, with network diagrams as an abstract part. You can also use some kind of Gantt chart as an abstract part, or you have maybe some kind of little bit narrative form, like in a mind map form, in general mind map setting as an infomural setting. You have some graph maybe facilitation, it's again some kind of mind map facility. You might also use some kind of force, good force and bad force field diagrams in order to represent this kind of setting. As an abstract form you have maybe some known ribbon chord diagrams or some parallel coordinates diagram or some parallel sets or some pictogram charts or some pie charts, how you develop in the classical setting with Excel. You might represent things also in a hyperbolic form, as in hyperbolic tree for instance, that shows also the importance of different parameters. You might use also, like you do it in geographic layers. So in this case you say, okay fine, I have a first layer that is the surface layers, and you have built something on the surface, and finally you can represent it, and then you can say, okay fine, I'm using the layer maybe 1, 4, 6 and of course 8 for the representation in the map whenever I need this kind of consideration. You can also develop things like a PERT chart, developing things, and then you have again a graph starting with an initial point and ending at an end point. You can have also some curves that display maybe some specific meaning, for instance a hype, like the Gardner diagrams are using it. You can have also what we use for an exemplification of learning. You might have some kind of computer integrated management system that uses a lot of sources and finally computes a number of results that is nothing else as a funnel diagram. You can have cognitive mapping diagrams. You can have something like this house of quality, where you show finally what kind of qualities the inner part has according to this representation. You can also use flowcharts. Some abstract visualization models are point maps, population pyramids, proportional area charts, radar charts, radar column charts, and also Sankey charts. Continuing with abstract, you have span charts, staked area graphs, staked bar graphs, stern and leaf plots, stream graphs, sunburst diagrams. Or you can say, okay fine, you can also make some kind of pattern for the WH framework, why, how, where, and then in this case you have now some kind of argument map. You can use the classical magic quadrant part that is really a little bit misleading, but anyway it's a good thing. You might have line charts or life cycle charts, or let's say some categorization of the life cycle. As an abstract model, you can have again tally charts, timetables, tree diagrams, tree maps, violin plots, word clouds. You might also use Sankey diagrams or risk process evaluation maps somehow. Or you have maybe road mapping, information models. Or maybe you use a story template, like you show this castle structure, and then you say, okay, fine, this comes into the castle, this is going out from the castle, and maybe the castle is properly supported. You can use some kind of process event chains, how we do it in business process modeling in the SAP setting. You might use parallel coordinates. That means in this case you have a coordinate system that shows different developments, maybe over time, and of course you use a number of coordinate sets for the y coordinates. You might have perspectives diagrams. You might have organigram syntax, or let's say you use a pie chart, or you use something that shows whatever is in time made using different colors depending on what kind of meanings colors have. There are some typical things: supply demand curves, stakeholder rating, and stakeholder rating in a different form. So you show here whatever is given there. Or is it the same? And then in this case you have a strategy canvas, a strategy game board, or a scenario matrix. And you can have also some kind of performance charting, or a cone tree in the park, maybe a form to show you what kind of impact something has. You can go also for organigrams or for patronet representation, showing the control in a system. You can have also stakeholder diagrams, who is guilty for what. You can specify also system dynamics based on some kind of dynamics models, or you can use what Porter has been developing as 5 forces. You have maybe a Porter value chain that gives you an evolution of a product making, or an evolution of some business. That means in this case you have a 2-dimensional plot again. You can have scatter plots or tree schemes. You have maybe some kind of metaphor you are implementing, maybe a tree, maybe air, maybe wind, whatever you use there. And you might have also some kind of interconnectivity diagrams, let's say placed as a classical circle with some connectivity segments. You can have some kind of business strategy maps, or you use some kind of strategy groups, or you let's say use some kind of tree maps for use, how we use it now with our special interfaces by smartphones. Or you can use also some kind of Thalheim diagrams for reasoning about causes. You can use also some kind of differentiation, that you say what kind of the system is soft, and what kind of the system is, let's say, more harder. And you have this kind of soft system structure. You can have also a table where you say, okay, fine, something like SBU is taken against the competencies you have to use there. Venn diagrams is a very popular form to represent at least 3 sets interconnectivity. You can use it also as in Venn Gauge banner endurance. We are using in UML swim lane activity diagrams stating which kind of responsibility is taken at which time according to the requests of the other partner. You can have a timeline diagram where you have a timeline, and then you say, okay, fine, these and these and these activities must be fulfilled, maybe in parallel, maybe in one after another. Then you have some tabs diagram. You can have a Tukey box diagram. You can again visualize something like a temple that shows the different parts, how we are using it also in the model of our model, or in the model of our model notions, better saying. Trickle diagrams show you the impact some figures have somewhere. Semantic networks are widely used nowadays in our data and science business. Yeah, it shows you interconnectivity. A very old method is to show a square of opposition, what is opposed and what is the specialization and what is in this case opposed to that one. That means my dog and my cat are opposing each other. I have here my dogs and my cat, and in general dogs and cats have this kind of bad, let's say, relationship. You have some curve diagram with some annotation what each point means in a two-dimensional setting. And then in this case you have, besides these very different, various visualization methods, nothing else as models for representation. And in specific forms these are visualization models. I have been showing you already with models about visualizations, the geometrical models displaying some kind of formula in a better form, so you can reason on the properties of that figure in a better way. Okay, this concludes now this a little bit longer chapter of this course. Next, I will go to a little bit shorter chapter, but not less important. We have to distinguish the background that comes from somewhere to our models. We have maybe to consider also the methods that are somehow inherited, and for this reason it is good to have some insight into the structure, the architecture of a model that is consisting typically of a deep model that is accepted in some area for some kind of applications, with maybe some method setting, with some basis and grounding. We call this deep model. And the normal model that is now our adaptation to the specific features we have to represent due to our origins, due to our interest. And in this case we have to differentiate both. For this reason I'm talking now in the next lecture about lengthening and biases, deep modeling as an economic principle, origins of normal models and the model background, and also about the matrix of a model. The matrix integrates deep model and mold into a common setting we should use. That is now this part of the lecture. I hope you have anything what you need to get here, and I will now stop.